Possible causes of fuse blowing include capacitor bank failure. Despite passing the Hippot test, one or more capacitors in the bank may have developed an internal fault during operation, leading to a short circuit and excessive current. Incorrect wiring may be the cause. Improper connections or loose terminations within the capacitor bank or its grounding system could cause arcing and fuse blowing. A ground fault may exist. A ground fault in the phase B conductor or within the capacitor bank itself can allow high current to flow, triggering the fuse. Overvoltage may be the culprit. A surge or transient overvoltage in the line could have exceeded the voltage rating of the capacitors, causing them to fail. Resonance is another possibility. If the capacitor bank is connected incorrectly or in combination with other resonant elements, it can lead to excessive voltage buildup and fuse blowing. The failure of the fuse on phase B may have created an unbalanced voltage distribution, causing the voltage on phase A to rise beyond its limit and triggering the fuse. This is known as cascading failure. The restoration of phase B could have caused a transient overvoltage that exceeded the voltage rating of the capacitors in phase A. Capacitor bank overheating can occur. The excessive current flow during the phase B fault may have heated the capacitor bank, compromising the insulation and leading to a failure in phase A. It is recommended to isolate and inspect the capacitor bank thoroughly for any signs of damage or loose connections. Check the grounding system of the capacitor bank and align for proper continuity and effectiveness. Perform voltage measurements to verify that the voltage distribution is balanced and within acceptable limits. If any faults are found, repair or replace the damaged components accordingly. Implement surge protection devices to prevent overvoltage events that could damage the capacitors. Consider performing a detailed power system study to identify potential resonance issues and mitigate them accordingly. Let's elaborate on these points. Firstly, capacitor bank failure. Capacitors, like any electrical component, have a finite lifespan and can fail due to various factors such as aging, voltage stress, temperature variations, and manufacturing defects. A Hippot test, while useful, only assesses the insulation strength at a specific point in time and may not reveal latent defects that could manifest during operation. Internal faults within a capacitor can range from gradual degradation of the dielectric material to catastrophic short circuits. When a capacitor fails internally, it can draw excessive current, leading to fuse blowing. It's crucial to visually inspect the capacitors for signs of bulging, cracking, or oil leakage, which can indicate internal damage. Measuring the capacitance and dissipation factor of each capacitor can also help identify deviations from their specified values, suggesting potential degradation. Secondly, incorrect wiring. The proper installation and connection of a capacitor bank are essential for its safe and reliable operation. Improper connections, loose terminations, or incorrect wiring configurations can create high resistance points, leading to arcing and overheating. Arcing can generate significant heat and ionization, further degrading the insulation and potentially causing a short circuit. Loose terminations can also create intermittent connections, leading to voltage fluctuations and current surges which can stress the capacitors and contribute to fuse blowing. It's important to ensure that all connections are properly tightened and torqued according to the manufacturer's specifications and that the wiring conforms to the relevant electrical codes and standards. Thirdly, ground fault. A ground fault occurs when an unintended current path is established between a live conductor and ground. In a capacitor bank, a ground fault can occur due to insulation failure, contamination, or physical damage. When a ground fault occurs, a large current flows through the grounding system, potentially tripping protective devices such as fuses or circuit breakers. The magnitude of the ground fault current depends on the system voltage, the impedance of the fault path, and the grounding configuration. It's crucial to have a properly designed and maintained grounding system to ensure that ground fault currents are safely conducted back to the source and that protective devices operate quickly to clear the fault. Ground fault protection devices, such as ground fault relays, can be used to detect and respond to ground faults, minimizing the risk of equipment damage and electrical hazards. Fourthly, overvoltage. Overvoltages are transient voltage surges that exceed the normal operating voltage of a system. They can be caused by various factors such as lightning strikes, switching operations, equipment failures, and harmonic resonance. Overvoltages can stress the insulation of capacitors and other electrical components, potentially leading to premature failure. The voltage rating of a capacitor is the maximum voltage that it can withstand continuously without damage. Exceeding the voltage rating, even for a short period, can weaken the dielectric material and reduce the capacitor's lifespan. Surge protection devices, such as surge arresters, can be used to divert overvoltages away from sensitive equipment, protecting them from damage. Surge arresters are typically installed at the incoming power line and at critical equipment locations. Fifthly, resonance. Resonance occurs when the inductive reactance and capacitive reactance in a circuit are equal, resulting in a high impedance and potentially excessive voltage buildup. In a capacitor bank, resonance can occur due to the interaction between the capacitor bank and the inductance of the power system. The resonant frequency depends on the capacitance and inductance values. If the resonant frequency is close to a harmonic frequency present in a power system, it can amplify the harmonic voltage and current, leading to capacitor overheating and fuse blowing. To mitigate resonance issues, it's important to carefully design and select the capacitor bank parameters, taking into account the system impedance and harmonic content. Damping resistors can also be added to the circuit to reduce the amplitude of the resonant peak. A power system study can help identify potential resonance issues and determine the appropriate mitigation strategies. The failure of a fuse on phase B may have created an unbalanced voltage distribution, causing the voltage on phase A to rise beyond its limit and triggering the fuse. This cascading failure happens because in a Y-connected capacitor bank, the voltage across each capacitor is dependent on the voltage of its respective phase. When a fuse blows on one phase, it removes the capacitor from the circuit, which can lead to a redistribution of voltage among the remaining phases. If the voltage on phase A rises excessively, it can exceed the voltage rating of the capacitors on that phase, causing them to fail and the fuse to blow. This cascading effect can be prevented by ensuring that the capacitor bank is properly balanced and that the fuses are adequately sized to handle the voltage and current fluctuations. The restoration of phase B could have caused a transient overvoltage that exceeded the voltage rating of the capacitors in phase A. When phase B is restored, it can create a sudden change in voltage and current, which can generate transient overvoltages. These overvoltages can propagate through the power system and reach the capacitor bank, potentially damaging the capacitors and causing the fuse to blow. The magnitude of the transient overvoltage depends on several factors, including the system impedance, the switching speed, and the presence of other electrical equipment. Transient voltage suppressors can be used to limit the magnitude of transient overvoltages and protect sensitive equipment from damage. Capacitor bank overheating may occur. The excessive current flow during the phase B fault may have heated the capacitor bank, compromising the insulation and leading to a failure in phase A. When a fault occurs on phase B, it can cause a large current to flow through the capacitor bank, which can generate heat. If the capacitor bank is not adequately cooled, the temperature can rise excessively, potentially damaging the capacitors and reducing their lifespan. Overheating can also degrade the insulation of the capacitors, increasing the risk of failure. It's important to ensure that the capacitor bank is properly ventilated and that the ambient temperature is within the specified limit. Temperature monitoring devices can also be used to detect overheating conditions and initiate appropriate actions such as shutting down the capacitor bank. Now, let's review the recommendations again. First, isolate and inspect the capacitor bank thoroughly for any signs of damage or loose connections. This involves visually examining the capacitors, fuses, connections, and wiring for any signs of wear, tear, or damage. Look for signs of bulging, cracking, or oil leakage in the capacitors. Check the fuses for signs of overheating or burnout. Inspect the connections and wiring for any loose terminations, corrosion, or insulation damage. Use a torque wrench to ensure that all connections are properly tightened according to the manufacturer's specifications. Second, check the grounding system of the capacitor bank and the line for proper continuity and effectiveness. The grounding system is essential for providing a low impedance path for fault currents, protecting equipment and personnel from electrical hazards. Use a multimeter to measure the resistance of the grounding system, ensuring that it is within acceptable limits. Check the grounding connections for any corrosion or loose terminations. Ensure that the grounding conductors are properly sized and installed according to the relevant electrical codes and standards. Third, perform voltage measurements to verify that the voltage distribution is balanced and within acceptable limits. Use a voltmeter to measure the voltage on each phase of the capacitor bank, ensuring that they are balanced and within the specified limits. Check for any voltage imbalances, which can indicate a problem with the capacitor bank or the power system. Investigate any voltage fluctuations or transients, which can indicate a potential overvoltage condition. Fourth, if any faults are found, repair or replace the damaged components accordingly. If any capacitors are found to be damaged, replace them with new ones that meet the original specifications. If any fuses are blown, replace them with new ones of the correct rating. Repair any loose connections or damaged wiring. Ensure that all repairs and replacements are performed by qualified personnel and that they comply with the relevant electrical codes and standards. Fifth, implement surge protection devices to prevent overvoltage events that could damage the capacitors. Surge protection devices, such as surge arresters, can be used to divert overvoltages away from sensitive equipment, protecting them from damage. Install surge arresters at the incoming power line and at critical equipment locations. Ensure that the surge arresters are properly sized and installed according to the manufacturer's specifications. Periodically inspect the surge arresters to ensure that they are functioning properly. 6. Consider performing a detailed power system study to identify potential resonance issues and mitigate them accordingly. A power system study can help identify potential resonance issues, harmonic problems, and other power quality concerns. The study should include a detailed analysis of the system impedance, harmonic content, and load characteristics. Based on the results of the study, appropriate mitigation strategies can be implemented, such as adding damping resistors, tuning the capacitor bank, or installing harmonic filters. The power system study should be performed by qualified engineers with expertise in power system analysis and design. In addition to these recommendations, it's also important to consider the following factors. Regularly inspect and maintain the capacitor bank to ensure its safe and reliable operation. Keep accurate records of all inspections, maintenance activities, and repairs. Train personnel on the proper operation and maintenance of the capacitor bank. Follow the manufacturer's recommendations for maintenance and testing. Implement a robust safety program to protect personnel from electrical hazards. By following these recommendations and considering these factors, it's possible to troubleshoot and resolve capacitor bank fuse blowing issues and ensure the safe and reliable operation of the power system. The information provided is for general guidance only and should not be considered a substitute for professional engineering advice. Always consult with qualified electrical engineers and adhere to applicable electrical codes and standards when working with capacitor banks and other electrical equipment. Remember that electrical work can be dangerous, and it's important to take all necessary precautions to protect yourself and others from electrical hazards. Always to energize and lock out equipment before performing any maintenance or repairs. Use appropriate personal protective equipment, such as insulated gloves and safety glasses. Follow safe work practices and procedures. If you're not comfortable working with electrical equipment, hire a qualified electrician.